Hey, IB Environmental students, we're starting acid deposition, which is topic 5.8. This is going to be optional. We're going to do a quick review of basic acid chemistry. You don't need to write this down unless you think you really need it. Okay, so acids are going to be things that have a high concentration and a lot of hydronium ions, which are hydrogen plus ions. And we need to remind ourselves what the pH scale is like. 7's neutral, that's what we think of regular water, where 1 is the most acidic and 14 is the most basic. This scale is logarithmic, so actual small changes are rather large changes. You should ask me if you don't really know what logarithmic means, and I can work with you separately. This is the one thing from this slide you definitely probably want to write down, that normal rainwater is about 5.6. It's not our normal neutral water amount. And when precipitation is considered acidic or acid rain, it's usually less than 5. And for a reference point, lemon juice is around 3 or so, right? So this is not super acidic. We are going to briefly talk about buffers. Buffers are things that are weak acids and bases. They're going to try to add, they're added to make more water or make the pH of the solution more neutral. So they're going to try to keep the acidity in equilibrium, and they're going to be related to a lot of our management strategies. Okay, let's move forward. Sources of acid deposition, 581. So those main sources are going to be coal-burning power plants, smelters, which usually are working with metals, your cars, your individual cars at home, and industrial plants of whatever type. And the major pollutants they're going to be releasing are things that are based in sulfur and oxygen, and things based in nitrogen and oxygen. And we refer to those as SOx and NOx because it's cutesy and a really nice way to remember, SOx and NOx. The X is referring to, usually, sometimes we can think this could be any sort of number. It could be a 2, a 3 at the end, 2 or 3 at the end. Most of the time, they're going to be sulfur dioxide and nitrogen dioxide too. And that's what we're going to see on this next slide, where the starting materials are the primary pollutants that we're going to be focusing on are sulfur dioxide and nitrogen dioxide, primary being that's what's actually emitted into the atmosphere. Secondary pollutants, remember, are things that have gone through a chemical reaction. So we're going to learn about 2 different types of main deposition, which are wet and dry. Let's start with wet. Wet is meaning, well, wet, related to water, right? So these things, SOx and NOx, are going to mix with water through a chemical reaction and form 2 different types of acid. And those major types of acid are nitric acid and sulfuric acid. Those are really important. They're not in yellow, but I would really write them down. And that's going to form precipitation of many different types. Precipitation could be rain, is what we're used to hearing for acid rain, or it could be snow even, or water vapor or fog. Now, wet deposition, notice, can be in the atmosphere for up to 4 to 14 days from the time it was originally emitted from whatever source, like an industry. And because it's up there so long, it can kind of move through the air and through wind pretty far away from its original source. That's compared to dry deposition, which is never mixing with water, and it's just like dusty particulate matter in the air, and those are going to be SOx and NOx as well, these 2 words. And they don't move very far from their original source because they're only in the air for 2 to 3 days. And that's going to relate to what our next topic's all about. Here's the actual chemical reactions. If you're curious, you just need to know the basic overview about how SOx and NOx become acidic. So don't worry too much about this bottom diagram. Okay, our next topic is about regionality of acid rain. Is it regional or is it global? And what you'll notice from this figure is that some of the areas aren't colored in, and that's because acid rain is regional. The green is going to be areas that have sensitive soils, which make them more likely to have issues in their soils from acid rain or acid deposition. The yellow areas are having a lot of air pollution due to the industries that are in that area mostly, and other factors. And then the red are areas, because of some of these issues, that now the lakes and the rivers are really at risk. And we're going to learn some of the reasons why. Another image here that's going to relate to our case study, we see a lot of coal plants where they're power plants for based in coal, and those are the red dots, and they're going to be highly related to how much red or yellow colorings on this map, and more red and yellow means more acidic. And there's a big pattern. The area that's darkest here is really close to this area that's near the Ohio Valley, right over here. That's our case study. And the wind brings over to even up north in northeast part of the America to make that part acidic, even though there's not a ton of power plants there. Because we can notice there's some pretty distinct differences between where it's strong acid rain and not, we can say that this is a regional problem. A lot of it's due to air circulation, especially wet deposition stays in the air for a while, and areas that are downwind, especially from factories, are going to have a lot of issues. And especially if it's near an urban area, urban areas are going to really deal with the dry deposition that only stays near its source. The case study we're going to focus on is eastern U.S. We saw that especially the Ohio River Valley, there were on that up right corner of the U.S., there's a lot of industry and like the coal power plants, and the sulfur dioxide produced there is going to affect even northern states that weren't necessarily producing the pollutant in the first place. And this statistic's amazing. Look, we have the acid rain in that area is tremendously lower than natural precipitation. Even what we were saying, acid rain just has to be under 5, but up down to 4.2, that's really acidic, knowing that this is a logarithmic scale and even small changes are pretty big. Now we're going to do other things about regional. The soil is going to impact regionality. Soils have buffers. Limestone is kind of like chalk, and same thing with calcium carbonate. They have this guy's calcium carbonate. When we add acid to calcium carbonate, it releases the calcium and makes it into water. That's what a buffer is. I'm not expecting you to know the details other than limestone acts as a buffer and makes things less acidic. So here we can actually see the calcium being released from the soil right here, and that means the area right here is a good soil buffer. Areas, though, that don't have this soil buffer, this extra limestone, are going to be sensitive. They're going to be the thinner areas. They might have granite instead of limestone as their bedrock. Or maybe they had limestone to begin with, but over time the buffer has depleted, and now the acid rain will make a pretty big impact. Now we're going to go to impacts on different types of organisms and areas. So impacts on plants is going to be highly important to our IA, so I would definitely keep track of this. Some direct effects, it's going to weaken tree growth, and I think that you could relate to primary productivity, especially this next bullet. The concentration of chlorophyll is going to go down. That's that pigment related to photosynthesis. We're going to lose some of our lipids, which are important for energy sources. Some of the needles, if it's a pine tree, are even going to fall off. Wow. Some of the toxic effects, when acid rain falls on the soil, extra aluminum will be released from the soil and it will be uptaken by the roots of the trees, and that's going to disturb root growth and function. We could add extra limestone or lime as a buffer to try to deter this from happening, but it could be toxic to the tree. Other things, as it hits the soil, we learned that calcium will be released, and all these other things will also start to be released because acid will change the solubility of different nutrients in the soil, and if these get released, that might make it less likely that bacteria can nitrogen fix, which is necessary for nitrogen to go into plants in the first place, and that's going to lower growth in general. Oh my gosh. Lots of effects that are no good. Aquatic plants are going to have a tough time too. It's going to lower biodiversity. We can see that different organisms here have different kind of resistances to a low pH. So for instance, clams can only be in this more neutral pH, like 6, and as it gets more acidic, dunsies. So that's a good indicator species. Although because acid will change solubility, it might make turbidity actually go lower, which is kind of ironic. We might see white moss on the bottom, which is an indicator of a problem. And we might have more dissolved metals, which are toxic. So really what's interesting is acid will change the solubility of different things that either will release things that are good and they're no longer available to places, or they'll release things that are bad, which we don't want to be available to things. No good. So once again, aluminum's gonna be released as a soluble item, and similarly, like plants, it's no good to fish as well because it's going to suffocate them, and they'll no longer be able to regulate the amount of salt they're intaking and outtaking. That's very related to osmosis for the IB biology students here. Case study, in the U.S., there's 9,000 lakes that are threatened. That's called acid shock. No good. Effects on humans, we're not focusing on this too much. This is unlikely situation because it's not a strong acid, right? So this is kind of a joke. Things, it's going to potentially increase bronchitis and asthma. It could give us toxic chemicals in our drinking water. Remember, it's leaching out all those chemicals because of the solubility. It could damage our statues and our cars and all of the things we care about because we're materialistic. It can make it so the atmosphere visibility is gross. That's the dry deposition. And we might lose economic profits because of all these things that are going away. Remember, natural capital, people are depending on these things for their livelihoods. Here's a cruel example of the effects on buildings that was listed in the previous slide. Yuck, no good, creepy. But this would have happened over hundreds of years. It doesn't happen in an immediate amount of time. And the real problem is, remember how limestone was a buffer? A lot of these statues are made of limestone, so they disintegrate fast. Now on to management strategies, which is our last objective. We're going to go through each of the major types. So we'll start with replace, which is usually the best. We could just reduce private vehicles, right? Like, why can't we just use public transportation or carpool? Maybe it's because we don't want to sit with the other people we don't know, or I don't know, just get used to it. Meh. We could switch to low sulfur fuels. This is the coal industries calls this clean coal. This could be maybe something that they use scrubbers to get rid of the sulfur from the coal. Super expensive though, and it's not really clear if it works. And same thing, clean coal, remove the sulfur from before the combustion in the first place. So that's replace. This one's easier. Some of you guys also in your web quest thought just use renewable energy instead of this other stuff. That's an easy one to add to the list as well. Regulate. These would be things that would happen through legislation, which we know is hard to pass. Maybe we're required to not have as many private vehicles. Maybe that's something we could pass. That's not happening right now, of course, right? We could burn less fossil fuels. Maybe we're using alternative energy sources. Maybe that becomes a legislative issue. That's not happening at the moment, but maybe it'll happen in the future. Here's our case study in our U.S. It's not very specific. So in the U.S., we're coal rich, right? But those people who really need coal and their economy and livelihoods based in coal, especially in West Virginia, they're going to continue using coal because that's what their lives are about. And when they see and hear about the effects, they're not necessarily right by them, right? Because of the wind and those regional issues, a lot of times it's hard to see the impacts, and that makes legislation very difficult. So really, because this is regional, but it's kind of weird and moves around, we really need to have an international kind of push or a national push to get the cooperation that we would need on this, because it's a tough issue to really pass legislation. Lastly, restoration. This is our last slide. So the one that I've been hinting at, we could lime both lakes and soil. So here in this picture, this is Sweden. This helicopter is literally putting calcium carbonate or that limestone that's grounded up into the lake, so it acts as a buffer to the lake. So this is tough, right? Can we really get helicopters and this much ground up limestone if we have this many acidified lakes in for instance, Sweden? And 4,000 of them were really seriously damaged. If we add this limestone to them, maybe they'll get better. The same process pretty much can happen in soil. So yes, you can lime lakes, but we can also lime soil, and that would be more in like pellet form. But you have to like add it and stir it into the soil, which takes a lot of energy and could potentially take cars and stuff. So this is short-lived, it's expensive, and it's after the fact. So think about how many lakes that we have issues with in the U.S. Can we really afford to do this? No. And that's it. You guys made it. This was long because you have an eye in it, and I hope it was useful. Good job. I'm proud of you.